I will talk about cake division. Simple problem when there is a cake and it has several toppings and we want to divide the cake fairly, and we will see what fairness means. So the whole difficulty of the problem comes because agents have different preferences. As you see, there are various toppings and everybody doesn't like every topping equally. So why is the problem interesting? I mean, if the cake was a homogeneous thing like this, then we would just make as many cuts as the number of agents, equal length cuts, and we would be done with it. So everyone gets one piece and that's it. And of course this division is fair. Nobody is going to complain. They all got the same length piece. Now, this is where the problem starts, when the cake is not homogeneous like before, but it's heterogeneous. As you see, there is a vanilla part, there is a chocolate part, there are some fruits, and the agents have different preferences. And now the question is, how do we fairly divide it? So if we make these cuts, just like we were doing earlier, and make this kind of allotment. So the girl in green dress gets the green part, and the orange one gets the orange. The girl in blue gets the blue shaded part. Then question is this division fair? As you see, they have not received what they like, but they have received something different from their liking. And of course the division is not fair. And if we do it like this is a fairer division. Now the green girl likes fruits and she gets all the fruits. The orange one gets entire vanilla slice because she only likes vanilla. And as you see here, it's not a contiguous piece that everybody gets. The girl in blue actually gets two different pieces. And although the length finally adds up to possibly the same one, but it's not a contiguous piece. And this is not a coincidence. We will see that it is actually unavoidable. So why this problem becomes interesting is because preferences matter and the preferences are all different. But then, is it really an important problem? So as it turns out it is, and cake is just a metaphor. Actually, lot of things need a fair division. For example, dividing natural resources like water or land among various countries, states. Similarly, division of money or budget. All these things, there are competing agents and they want the central authority to be fair. As you see, even our central government, when they allot budgets, obviously there are people who complain about not being fair. This is a very difficult problem, so to say, and very important and unavoidable one still. So we will keep in mind that fair division of cake actually has lots of applications, but we will only talk about cake. So what do we have? Formally the model is like this. There are n agents and there is a divisible item denoted by a 0-1 interval. What I mean by divisible is we can just split it the way we want, anywhere. And how are the preferences of the agents given? So they are given as valuations vi, and for every non-negative interval xy, the valuation vi assigns a particular value. So there is vi of xy interval for every x and y. We will assume that the valuations satisfy these properties. One is additivity. So for disjoint x and y, if x has value alpha and y has value beta, and if an agent gets both x and y, then the value will be alpha plus beta. One can as well define other kinds of valuations, subadditive or superadditive. But these are the simplest ones to deal with. These are additive valuations. And another one that we will, assumption that we will make is that of divisibility. So here we will assume that if we are given any subinterval x of 0-1 and any fraction lambda, and we ask that I want a lambda fraction of x, then there is always a y which we can find out. There is at least, it at least exists. So there is always a y which is a lambda fraction of the total value of x. And so here, if this is an x and we want a lambda fraction of it, then this star q1 is the lambda fraction. So it always exists. So this is kind of a continuity sort of requirement. So the cake doesn't have any non-discrete or indivisible topping which suddenly changes the value if the topping is included or not. So there is this is kind of a underlying continuity assumption. We will also assume that for each agent the value of the entire interval is 1. An agent gets the whole cake, the agent assigns value 1 and every other value will be possible smaller. Any questions so far about the model?
Values are always positive.
Say it again.
Values are always positive.
Values are always positive. So, more formally, the valuation function vi assigns a positive value to every piece, and for any x we can just find vi of x as the integration of the value density function. Just like we have continuous probability distributions, here there is a density function and the value of an interval is obtained by integrating it over the particular interval. So now coming back to the question of division. A division or allocation is a partition of the cake, which is the 0-1 interval, where each AI is a piece of cake. Nothing remains unassigned and everything goes to exactly one person. So this is, for example, an allocation. The blue part shows allocation A1, the yellow one shows A2 and orange one shows A3. Now there are two notions of fairness that are typically defined. One is proportionality. So since every agent assigns a value 1 to the whole cake, what the agent wants as a measure of fairness is a 1/n value portion of that cake, where n is the number of agents. So everybody wants a proportional share, but proportionality is not in terms of length, but in terms of the value that the agent assigns. So here the agent will not care what everybody else gets. So if somebody else gets a higher share in the view of this agent, then that agent is not going to. And there is another notion we will see, that is envy-freeness, where the agent actually looks at what other people get and possibly envies other agents if they have a higher valued piece. So what we need for envy-freeness is that the value that an agent assigns to her own piece is at least as large as the value that she assigns to someone else's piece, everyone else's piece. So agent J's perspective according to the valuation Bj could be completely different, but this we want to happen for every pair I and J. So as you see, these are fairly old notions, much before I think we had computer science programs. So if we look at the relation between them, then envy-freeness implies proportionality, and it is not very difficult to prove. You can just write all these inequalities and add them up, and you will get that an envy-free allocation is always proportional. But the other way around may not be true, because everybody gets proportional share in their own view doesn't mean that somebody else won't get a higher share in their own. Any question about these definitions? And we, obviously we cannot specify the value of every interval because there are uncountably many of them. So how do we specify the valuation function? So the underlying model that we consider is the so-called Robertson-Webb query model. We assume that we have an oracle which tells us answers to these two queries. So we can ask these two queries. One is the evaluation query and another is the cut query. So evaluation query is of the form eval I xy, and we get the value of the xy interval in the view of ith agent as an answer. It's like a procedure that is or subroutine that is available. And the second query is cut query. So if we ask cut I x alpha, then it returns a y, so that starting from the point x, this query returns a point y, so that value of x y is exactly alpha in the view of agent I. So we will assume that we have these two kinds of queries we can ask and we can get answers. Okay, so simplest thing is when there are two agents. So this is called a cut and choose protocol. I think this we also implement in our own daily lives. That one agent does the cutting. So agent 1 cuts the cake into two equal valued pieces according to her. So now because these are equal valued for agent 1 is happy with either of them. And then agent 2 just chooses better of the two pieces in her view. So then, is it MVP? Yeah. Agent 2 thinks that she has a better piece because she got a chance to choose a better piece. And agent 1 anyway has both pieces equal valued, so this is MVP. And this is also proportional. And in fact, we can show that NV-freeness and proportionality are indeed equivalent for two agents. And beyond two agents, they need not be. It's a very simple protocol. How many queries did we need? Two, right? We have to ask agent 1 an a cut query, cut 1. So it can be implemented in Robertson web model, and these are the two queries we asked. Cut 1 0 comma half, which gave us a point y, so that agent 1's value for 0 to y is exactly half, and hence for y to 1 is also exactly half. And then we asked the eval query for agent 2 to identify the better piece. So this one query is enough because if eval to 0 y is less than half, then of course we can give the y to 1 piece because that is going to be more than half. So in two queries we are. So let's see a proportional cake division now for an arbitrary number of agents. So this is called a Dubin-Spanier procedure, and this is also a very intuitive procedure where a referee gradually moves a knife from left to right, starting from the leftmost point of the cake, and as soon as the piece to the left is worth 1 over n for any agent, the agent says stop, and then that piece goes to that agent, and the procedure continues with remaining agents and remaining portion of it. Here is a small illustration for 3 agents. The knife starts with 0, and whenever it reaches 1/3, if we are doing it for 3 agents, whenever it reaches 1/3, one agent will say stop. This portion 0 to this point is 1/3 for that particular agent. The agent gets it, it is of course proportional share, and the knife then again moves, and there are 2 remaining agents. One of them will say stop, and again it crosses 1/3 for the remaining portion. Like from here to here should be 1/3 of the portion. So this 1/3 goes to the second agent, and the entire remaining part goes to the third agent. Is it proportional?
Yeah.
For 2 agents, or in general n-1 agents, of course it is proportional because they say stop only when it is proportional share for them. And for the last agent, the pieces that were lost were not more than 1 over n anyway. So since n-1 of them are lost, the leftover value is at least 1 over n. So this is indeed proportional, and it may not be NV-free because if the last piece left is quite large in other agents. So agent except the last one gets 1 over n, and the last agent possibly gets even a larger share, but at least 1 over n.
Is it not anything just because of the last? Other people might also be unhappy with this.
So our goal here is proportionality.
Right. So it's proportional except for the last. What about you had a you said something about NP?
So this procedure will not give us NP division.
Right. And the problem with that problem with indefiniteness is not just the last person. It's also
It could be anywhere in between.
Yeah.
Yes. If the second agent says stop at like at a larger share in the view of first agent,
Right.
then the first agent can NP the second agent. It could be there could be NPs between any two agents. I mean NP bit from an agent who chose earlier to an agent who chose later. So this works only for proportionality. Question is how many queries, and this looks like a continuous procedure. We will need value of every interval. It looks like. Is that really the case? Can we do it? Yeah.
Can you repeat once?
Say it again.
Can you repeat once? What did you ask?
I asked how many queries will we need? Because after all, we want this to be an algorithm. So if we have to, certainly we can't really move the knife continuously in an algorithmic sense, because you can't really look at value of every.
First cut we need like
You have
n
to
cuts.
ask every person the
Then n minus 1 cuts.
like different evaluation of one by n and n cutting gap. Again, like, at each step there will be n queries.
Yes.
So n into n plus 1.
Yeah. So roughly n square kind of.
Yeah, it's
That's right. So for example, we will ask a cut query for 0, 1 over n for every agent, so all n agents. So n queries will give us the first piece, whichever is the smallest, we will give that piece to that agent. And then this is what we will continue later. Essentially, order of n square queries is what we will do.
So in the second step here, we aren't choosing which agent.
We have to go over every agent and ask what is your 1 over n piece starting from this point. And whoever gives the smallest interval, like the leftmost point, we will go give that piece to that agent, because that agent would have said stop before anybody else.
So we could have binary search.
Yes, so that's right. In fact, optimal is n log n, and there is a lower bound n log n as well. So this is the whole landscape of results. For 2 agents, 2 queries suffice. Order n square suffice as we just now concluded. But the right answer is n log n, which is right. There is a lower bound, and that's fairly recent in fact. Yeah, n log n is necessary and sufficient. Okay, so this is a well understood, at least for additive evaluations. Move on. Any questions about
for the
proportionality?
n log n part. Do you like actually do what we do in binary sort, or is there like same idea but some different process to it? Do you cut the cake in like half valuation to someone and then like work with both different pieces, or how is it?
Yeah, it will be some variant of binary search essentially. Okay, so now let's come to NVPness, and things suddenly become a little more complicated, as we will see. Recall that NVPness requires that every agent thinks her piece is at least as good as anybody else's. And this result was proved in 2 different works, that NVP division indeed exists for any number of agents. This was really a non-constructive proof, and it uses Sperner's lemma. So let me talk a little about Sperner's lemma. This is a very nice lemma, and it has found a lot of applications. And on the face of it, it doesn't seem to have anything to do with cake or division or anything. But it's a very nice combinatorial thing on its own. So here we have simplex and its subdivision into elementary simplices. So you don't know simplex, just see that it is a triangle. and it is subdivided into several triangles. It is done in a particular way in the sense that no edge starts from the middle of this. There is no undivided quadrilateral or larger polygon. So it's a fully triangulated. It is not necessary that you have to triangulate it like this. Any division into triangles is fine. And the lemma will hold no matter how you subdivide this triangle into smaller triangles. Now what we want is a so-called Sperner coloring. Now what is a Sperner coloring? The main vertices of the big triangle, they get different colors. So here you see that they have purple, red and green color. And now we have to color the boundary vertices. That there is a constraint that whenever we look at a boundary, those vertices should get one of the two colors which are present at the ends of that boundary. So the one that I have marked should get, every vertex should get red or purple color. No matter how it's okay. I mean, whatever way we want to assign, we can assign. But it cannot get, any of these vertices cannot get a green color. So here is the assignment of colors that satisfies this constraint. So everything here gets purple green, everything here gets red green, everything here gets red and purple. And now coming to internal vertices, we can absolutely assign any color that we want, any of the three colors. So like this. And this is a valid Sperner color. Now what Sperner's lemma says is that any Sperner colored triangulation has a fully colored triangle, meaning all three vertices of that triangle get a different color. Here I have highlighted one. You can possibly find more if at all. There is at least one. Any questions about the coloring? So I will give a proof sketch of this lemma before we relate it to cake division.
How to color the triangles inside?
Anything, any of the three colors can be assigned to the internal vertices. Only the boundary has a constraint. Everything else you can color whatever you want. So this is, I am just doing this in 2 dimensions with a triangle. But this everything holds for n dimensions. You have to take an n-dimensional simplex and subdivide it into smaller simplexes. Everything works. You will use n colors if there are n corners to that simplex. So I will give a proof sketch. So we will call every elementary triangle here a room, and we will fix any 2 colors. So let's say purple and red. So every edge which has one vertex colored with purple and another vertex colored red as a door. So because I chose purple red combination as a door, these are the doors of this particular color. And as you see, the number of doors on the boundary is odd. And of course, out of the 3 sides of the big triangle, these 2 cannot have a purple red combination. Only one side can have a purple red combination, and there are always an odd number of doors. Does everyone see it? So if you look from the top, the red color sometimes has to change to purple, at least here. So if it is red, and finally purple, then this is the only door. Otherwise, whenever you change to purple, it may happen that you continue with purple again, like red and then purple everywhere. In that case, the top edge will be the door. So there is an odd number. And in between, if you switch from purple to red, you have to again switch from red to purple. So if you add more doors, more than one, then they will always be added in pairs. You will always have an odd number of doors. Now look at the rooms, that is the elementary triangles. They can have 0, 1 or 2 doors. So for example, here is one with 0 door. These are the ones with 2 doors. Can any triangle have 3 doors? Because you can't have purple red combination on all three edges. Now here are some examples. So these are kind of elementary triangles which have 0 doors. These have 2 and this one has 1. So as we see here, if we find an elementary triangle which has only 1 door, then that is the triangle that we want. So we have to essentially show that there is always a triangle that has only 1 door. So this is the one that we are looking for. So how do we find, or how do we even tell that such a triangle which has only 1 door always exists? So just start walking along the doors. Start from the boundary, always start outside. Enter one of the rooms through 1 door. Now if this has only 1 door, the one that we entered, we are done because this is a fully colored triangle. Otherwise it has 2 doors because it had 1, it has to have another one then. Then we can exit through that door. So never repeat doors, always enter through 1 and exit through 1. So for those triangles which have 2 doors, we will always use 1 for entry and 1 for exit, so they will be used up. We will never enter the triangles which have 0 doors. And if we enter a triangle which has only 1 door, we are done. Okay, so either we reach a fully labeled triangle, that is we are stuck in the walk, but that's a good thing because we found a triangle which has only 1 door, which is fully colored, and then we are done. Or we exit from another door. Finally, it may happen that we just keep walking and we exit through another door at the boundary. This walk shows that we enter, but then we again come outside the triangle by following a sequence of doors. Are we stuck here?
Coming again to the next door.
Yes, and why will there be a next door again?
They are odd number.
Exactly. So when we use 1 for entry, we use another for exit, but this only consumes even number of doors on the boundary. So this we use for entry, then that one we use for exit. But what we showed was that there are always an odd number of them. So we will always have yet another door left for entry. So again start from a new door on the boundary, and there are an odd number of them. So here we can enter again from the leftover door, and then finally we reach a fully labeled triangle. Can we keep cycling within the triangulation itself without coming to the boundary? We can, yeah.
The finite number of triangles will be cut.
True, but if we had found a hexagon like this and a collection of doors like this, then it is possible to keep cycling, but such a door can never connect to the boundary because for the boundary we are only entering once, and hence we cannot complete the cycle coming out of the boundary. And once we enter from the boundary, there cannot be an internal cycle because every room has at most 2 doors. So I hope you can convince yourself that you will always, this procedure cannot stop without finding a fully labeled triangle. On the other hand, it has to stop because we are exploring different doors. Why can't we repeat a door in the second walk?
Why can't
Repeat the door in the second walk, like we entered from the top one. Why can't we come out from the middle one again? If we could do that, then we would be again stuck.
Yeah, because like we already used the door, so we are not using that door again. So you can't possibly be in the inside region that is enclosed by the doors.
Yes, so good. So we are entering through another door now. For every room that we traverse in our first trial or first walk, we have used them up, but then there is no third way of entering any of those rooms. So it cannot happen that we have gone through this room but we again enter it. That cannot happen because there is no third way to enter any room. Okay, so finally we must reach a room with 1 door, and that is what our fully labeled triangle is. So I hope you are roughly convinced that we will always have a fully labeled triangle because of this process. Now, how do we do cake division using this Sperner's lemma? So remember that we have cake as a 0-1 interval, and suppose we have 3 agents, just because we can only draw triangles and not larger symbols. And then we say an allocation is NP if every agent thinks her slice is as good as anybody else's. So this is how a division looks like. So 0 to x1 forms one cut, x1 to x2 forms another cut, and x2 to 1 gives another cut. So if you look at these lengths x1, x2, x3, then that is a cut. So every x1, x2, x3 will define a cut. What are the properties needed for x1, x2, x3 to form a cut? First of all, they should add up to 1, and every xi should be non-negative. So this is a space of all possible cuts that we have. And if we plot this in 3 dimensions, because we have 3 coordinates x1, x2, x3, we will see that all these points lie on a single place or a single triangle whose endpoints are labeled 1, 0, 0, 0, 1, 0, 0, 0. Those are the coordinates of the endpoints. And anything on this triangle is a point x1, x2, x3 with this property and of course non-negative. So basically every point in this red triangle defines a valid cut. Does it make sense? We are just looking at the cuts as a point in 3-dimensional space, and they nicely happen to lie on a triangle of this one.
So right now we are only considering the continuous base of division and not the magic formulas.
Yes, very good. So actually what we will get using Sperner's lemma, not get because it's not constructive, but what Sperner's lemma guarantees is that a connected cake division always exists. So when we finish seeing this connection, you will see that not only that it guarantees square division or NV-free division, it also guarantees a connected one. Okay, so now we want to use Sperner's lemma and fully colored triangle to get our cut. So this red colored triangle that we had, this is now our big triangle, and we will triangulate it with like the way we did for Sperner's lemma. So triangulate it into small triangles in whatever we want. The coordinates of the corners of the big triangle, they are 0, 0, 1, 0, 1, 0, 1, 0, 0. Note that this cut for example amounts to first piece having the entire cake and the other 2 pieces being empty. And similarly for the other 2. So the corners really correspond to the whole cake going into exactly 1 piece and 2 pieces being empty. We will use this fact in a while. Now we want to label the vertices not as a Sperner coloring, but we want to assign ownership to these vertices. So let's call our agents as ABC. To every triangle we want to we want to label every vertex of all these small triangles, so that every elementary triangle or small triangle gets all 3 labels. So if you see here, whatever elementary triangle you take, we get all 3 labels ABC on its corners. Why is it always possible? Is it
How are
always
you defining the vertices, points ABC? Like how
ABC are the names of the agents, and we are arbitrarily giving labels. We are arbitrarily giving these vertices one of these 3 labels. So we say that agent B owns this vertex, agent C owns this vertex, and so on. And what we want is that for every elementary triangle that we see, the 3 vertices of that triangle should be owned by different agents. Any question here? So this can always be done. I will not prove it, but you can find your own procedure to do this. So this is something I will leave at this point, and hopefully you can think and figure it out. It can always be done. This kind of ownership label. Note that this is not a Sperner coloring because that corner and this corner have AB labels, but there is a C in between. This is not a Sperner coloring. Now for this triangle that we generated, we want a spurner color. So how do we assign a color? So color of a vertex is the preferred piece of its owner. So this is the ownership labeling. Now the topmost corner is owned by agent A. So we ask agent A, what is your favorite piece if the division is 001? So here we are asking agent C, what is your favorite piece if the cut looks like 100, that is entire leg goes to the first piece and the other two pieces. Obviously anybody will prefer the whole cake rather than an empty one. This is a hungry agent's assumption. We will go with that. So clearly there the third piece is going to be liked by agent A, so the vertex will get a color 3. Here this agent is going to like piece 1, so this vertex has color 1, and that agent will like second piece, so this vertex gets color 2. I am just calling the colors as 1, 2, 3 now. Agents are ABC. So at any vertex of this triangulation, the ownership labeling tells us whom to ask for a preferred piece. At the corners, it is obvious that the 3 colors will be different because 3 different pieces are actually empty pieces, full pieces. What will happen on this boundary? Like let's say this boundary.
Since the third piece is always empty, no one will prefer it.
Yeah, it will always be true.
Exactly. So this third piece is empty throughout. Only the first piece gradually increases and second piece gradually decreases. So first piece increases from 0 to 1 and second one decreases from 1 to 0. So depending on the agent's valuation, whoever owns it, the preferred piece will be either 2 or 1. It cannot be 3 because 3 is empty throughout. So the boundaries are going to get this kind of colors. This will get only 3 or 1 and will get 2 or 1. This will get 2 or 1. But this is what we wanted for spurnal coloring. And we were okay with internal vertices having any color. Here also the internal pieces may have, we can't really predict who is going to prefer what piece for the internal ones. This is a possible coloring, and then we will have, I have not shown the colors, when whatever colors, and then there will be a fully colored triangle because of spurners. Okay, so spurners lemma parent is a colorful triangle or fully colored triangle. What ownership labeling guarantees is that when we look at that fully colored triangle, the owners are all different. So here, if you look at this triangle, agent A is going to prefer second piece, agent C is going to prefer third piece, agent B is going to prefer first piece. And so everybody prefers a different piece when you look at such a color. Any question? Are we done? Not quite. And why not? A triangle doesn't quite represent one cut. We said that every point on the simplex represents one cut. So what this triangle says is, whatever cut is represented by the purple point or corner of that corner, agent A prefers second piece for that cut. Now these two green and red cut points, they are nearby cuts, and the agents prefer different pieces at those cuts. So these are 3 cuts which are close to each other but not quite the same. So what we would like, ideally want, is to shrink the triangle to really a single point. Any question or comment? Yeah.
Like right now I said that let's on the side 2 and 3, no one will prefer cake 1 because it's empty. Why
Yes.
can we say the same for this, for when we iterate this process? In our new figure, the new triangle that we have.
New meaning?
Yeah, in this triangle, for the
No, this is just a piece of this triangle, a colorful triangle from here. we will do something different. But are you convinced that this is not quite the final solution that we would want? Because the triangle is not a single, but it's a collection of three nearby cuts where different agents prefer different pieces. We want to kind of shrink the triangle, but we will not triangulate that triangle further. So I have not drawn this. Here I will just give a sketch. So what we will do is we will make this entire triangulation final. So currently we are drawing triangles at say 0.1 interval. We will make it 0.05. Again we will be guaranteed a colorful triangle, but now the cuts will be closer to each other. Do it like 0.025 after that, and so on and so forth. So keep on shrinking the interval at which we form the triangles. So it's like earlier we have a coarse mesh, now we will have a finer mesh of triangles, another finer mesh, and so on. So this will be a continuous process in some sense. We will keep on having the intervals. It can never become zero, but what we have to say is that in the limit it will be zero, and at that time there will be a cut, because a colorful triangle always exists one of this time. When in the limit, like after doing this infinite time, whatever the shrinking goes to zero, the triangle size goes to zero in limit, and at that point we will have a cut where agents prefer different pieces. So it will be an NV-free division in limit, but not quite. We are never practically going to reach it. So if we want to use this in practice, it's a bit difficult for several reasons. So one thing is, of course, we cannot reach the limiting point in any finite number of iterations. What we can get is an approximate NV-free division. So if the triangles have some epsilon psi 10, like smaller triangulation was done at epsilon length intervals, then we would get some epsilon NV-free cake division. So that is what we can get in practice. But there is also another non-constructive ingredient here. What's that? Even for Sperner coloring is fine, we can do it in linear time in terms of number of vertices. But how do we find a colorful triangle? So that procedure can take again time, which is proportional to the number of elementary triangles. As you make the triangulation finer and finer, the number of vertices or number of elementary triangles goes up, and we are not quite going to get up. I mean, it's not going to be polynomial in the number of agents, but the time will depend on how fine our triangulation is. So this is also not a very nice polynomial time procedure. Also, another point here is that so the procedure will essentially depend on how fine our triangulation is, and so depending on how much approximation we are willing to tolerate in the NV-freeness, our running time will indeed depend on that. And of course, this we are doing for free agents. When we do it for n simplex, another n factor would add to all that, because there will be many more elementary simplices as we make it constant. So in general, this is not a constructive procedure, and the number of queries will keep growing. Not a nice algorithm. But any questions so far? Is everyone convinced that this gives an existential proof?
For 9%, we take the triangle in n-1 dimension and then color it.
Yes, so it's not a triangle, it's an n simplex, but yes, we have to take an n simplex, divide it into sub-simplexes and use n colors. And now the boundary will be, there will be different boundaries. It's not a single boundary when you go to n. There will be an n-1 dimensional boundary and n-2 dimensional boundary and finally 1 dimensional boundary and so on. So whichever dimensional boundary you are looking at, you have to look at its corners and assign only those colors. Wanted me to move on like this. Yes. Okay, so what this result shows is that NV-free cake division with connected pieces exists for any number of agents. And there is a later result by Strongquist, much later result, 1981, that there is no finite query protocol for connected NV-free cake division. So we would like to get an algorithm, but indeed we can't have one with finite queries if we want connected pieces. So since we don't want an infinite query protocol, it's not useful in practice. What we would have to settle for is a disconnected division, like I had shown in earlier examples. And here is a landscape of known results. So for cut and choose, again 2 queries suffice. For 3 agents, there is a variant of the cut and choose itself. So one agent will make 3 pieces. The second agent will take 2 better pieces for her and then make them equal by cutting off a small piece from the better of the 2 pieces. For second agent of the 2 pieces will be equal. The third agent will choose, and then whatever piece the second agent cut off, that we have to divide again. So that amounts to disconnected cake division. So for 3 agents itself, this selfish conflict protocol is there, but that doesn't give connected cake division, it will give a disconnected. And finite but unbounded protocol was shown in 1995 by Brands and Taylor. It was improved to this query complexity, n to the whatever. Those are 6 n's. And that was very recently, right, in 2016. The lower bound known is only n square. N square queries will definitely be needed. That is the upper bound we have. There is a really huge gap between them, which is okay. So for small number of agents like 4, and people try to see what is the exact query complexity. So that is still the ongoing research direction people are pursuing. There are results known for very restricted valuations. I will not share. Okay, so this was all about cake division, and as you see, there is a huge gap. We don't know how to close that right now. And I will talk a little bit about other things in pair division. So far we said that the cake can be divided in whatever way you want, and still we can't get connected division with connected NV-free division with small number of queries. When we have indivisible resources, that poses different challenges altogether. For example, if we want to do inheritance division, then we can't split house or let's say car, laptop, whatever, among agents. We have to give an entire piece to that agent. So if we have indivisible items and we want to assign or divide them among agents, again we cannot split the items, and hence NV-free division may not exist. Simplest thing is to see that if there are 2 agents and only 1 item, no matter whom we give that item, there will be an. So NV-freeness is out of question when we talk about indivisible resources. Here are others: lecture rooms, flats, vaccines, medical resources. These are examples of indivisible resources. Not only that, an NV-free division may not exist, which is very very obvious to see. It is also NP complete to determine if it exists in a given scenario, given set of valuations. So I am just stating a few things here, but we will not see the details of indivisible resources at all. Because NP-free division may not exist, people have proposed various relaxations. NP-freeness up to one item. You remove, every agent gets certain set of items. But if an agent hypothetically removes one item from another agent's bundle, then the bundle value goes down and the agent is NP-free towards that. EF1 and it has nice properties, it always exists, it is easy to work. There is a slightly stronger notion which is called NP-freeness up to any item. Agent I envys agent J, but we want the envy to go away when agent I removes any one item from agent J's bundle. This is called EFX, and again the existence is open beyond 3 agents. We don't even know whether it exists beyond 3 agents or not, let alone be the computational complexity of it. So even in indivisible resources there are all these open questions. There are other notions of fairness as well. I just considered 2 of them, proportionality and there are several others. Yeah, I think I will stop here and so thank you again. I have used the figures are entirely from other people's slides. I didn't draw a single one of them. They were kind enough to allow me to use them. Yeah.
Well, if you provide the consensus algorithm for 3 people was NP-free. Let's say person 1 cuts 3 pieces, and person 2 divides 2 of those pieces combined according to his own.
Not combined, it will be like this. So this is the entire K. This is visible. So agent 1 cuts in 1/3 according to, so these are cuts by agent 1. Now agent 2 doesn't combine these pieces. What agent 2 will do is to look at these pieces according to her own valuation, see which is the, so these are the, let's say 2 better pieces for agent 2. So these are better for 2. So 1 cuts, these are the better pieces for 2. Now agent 2 wants to be NP-free. So what agent 2 will do is take the better of the 2 pieces and trim it off so that these 2 pieces become equal for agent 2. So let's say this piece gets trimmed off, we will keep it aside. Now for agent 2 these 2 are equal and they are still better or at least equal to these. So agent 2 is now fine between any 2 of these. Now we will ask agent 3 to choose. So if agent 3 chooses one of these, it's well and good, agent 2 is fine with the remaining, agent 1 is fine with this one itself. If agent 3 chooses this, then it's a bit of a problem, but then because agent 1 always has one piece intact, like this piece was trimmed off, but this piece is intact, it is the same piece that agent 1 made. So agent 1 can then take this, agent 2 is fine with either of them, so agent 2 is take this. So this actually needs some 8 queries sort of. And then this trimmed piece we have to again subdivide. So they call it cake crumbs, eventually it will come down. Does that answer your question? Any other question?
We also study these questions in evaluation department.
Yeah, so slightly structured valuations are studied.
It's like some modularity.
I think so, but yeah, the problem is only going to be harder. I don't remember the exact results. I think what people would also be interested in is to look at some subclass of additive evaluations, if at all, and see if the problem becomes simpler.
Because for some of the real scenarios mentioned, evaluation functions do tend to have other properties.
Yes, and in fact, subadditivity is very natural to consider because beyond a certain limit, I may not be able to eat the piece of cake that I get. So, if I I get a too large a piece, then I may not be very happy with that. I mean, it may not be additive, like I am happy with one piece, I am happy with another piece, but combined together I may not be as happy because it's difficult for me to finish. So, there is also another completely different scenario where people consider, they call it burnt cake division, but what it means is the divisible resource is one that people don't want. They are like responsibilities, and less responsibility, better it is. So that is called burnt cake division, and that also turns out to be significantly more difficult than cake division. Anything else?
Like when you like to find the 3 cake division, we like took the like size of the triangle smaller and smaller. But like how can we be assured that like it will converge properly and then to a single point?
So the convergence one has to prove that it takes a little work to show the. I mean, convergence is fine, as in what one has to show is there will always be a colorful triangle, but the ownerships might change because now you might get a completely different colorful triangle. So what you have to show is you will have. Let me show this picture. So here we had this, right? So this had colors 3, 2, 1 and the pieces were preferred by C, B and A. Now when we get smaller and smaller colorful triangles, this permutation might be different. So you have to prove that because in one of these permutations will appear infinitely often, and that will be the convergent. So yes, convergence takes some more work. There are lots of fixed point theorems which are being used in fair division currently. So if you are aware of fixed point theorems, then Brouwer's fixed point theorem, or there is what is called as KKM lemmas. These are increasingly being used even for discrete fair division or division of indivisible items as well, not just divisible. There is a lot of literature on that in fairly like last couple of years.